Welcome back to Einstein Mechanics. Today we are going to solve the problems under stress and strain. So let's get started. Let's look at this example. A tensile test is carried out on a bar of mild steel diameter 20 millimeters. The bar yields a load of 8 kilonewtons. It attains a maximum load of 15 kilonewtons and breaks finally at a load of 7 kilonewtons. So in this question, we have three forces: the yield load, the maximum load, and the breaking load. So we are to find the tensile stress at the yield point, the ultimate stress, and the average stress at the breaking point. At the breaking point, the diameter of the neck is 10 millimeters. So let's get started. So from the question, I have my diameter D to be 20 millimeters. I like working in meters, so D will be equal to 0.02 meters. And I can also state that my area can be calculated because I have the diameter. So my area here can be pi d square on 4. We assume it to be what? Circle. A circular surface. The forces are acting on a circular surface. So from this, we can calculate the area as pi d square on 4. We have it here already. Let's find A. What's the diameter? 0.02 square on 4. So my area will now give me so this is my area for the bar. So 1, at the first point, the tensile stress at the yield point. At the yield point, this is it. The bar yields at a load of 8 kilonewton. So the force at the yield point was 8 kilonewtons. But remember, we have the same area. So stress at the yield point is the same as force over area. We can put in our values. The yield load the yield stress now is giving me 25.46 megapascal. Remember, megapascal is times 10 raised to the power 6. So 25.46 megapascal. That will be the stress at the yield point. The force was 8 kilonewtons. Let's go to the 2. The ultimate stress. Remember the same area. The ultimate stress from the question, it attains a maximum load of 15 kilonewtons. Ultimate or maximum, we can use this force because it's the maximum load and we have to find the maximum or the ultimate stress. So at the ultimate, the F, the force was 15 kilonewton, the same area. So stress at the ultimate, so we can calculate the ultimate U for ultimate to be 15 kilonewtons on the same area here. the area. So the area is 3.141 times 10 raised to the power negative 4. So my ultimate stress is giving me megapascal. So 47.7 megapascal. Remember the area was the same for the yielding load and it was the same for the maximum load, but it finally break at a load of 7 kilonewton. But look at this. The average stress at the breaking point, if the diameter of the neck is 10. So at the breaking point, if you look at the episode 2, I explained why this neck is reducing to 10. So at the breaking point, the diameter is no longer 20 millimeters, but rather 10. So we are going to estimate another area before we can find the average stress at the breaking point. But the force is 7 kilonewtons. Are we good? So let's find the area where the diameter is 10 with a force of 7 kilonewton and find the stress at the breaking point. Now, at the breaking point, the neck is 10, the diameter of the neck is 10. So we have our new D, diameter is 10 millimeters, which is 0.01 meters. So let's find the area. So from this, the area at that point, pi d squared on 4 equal to, we have our pi, our new d is 0.01 square on 4. So the area is now giving me 7.8539, sorry, negative 5 meter square. Therefore, the breaking stress, the average breaking stress at the breaking point. So the stress at the breaking point can be the force still over the area, the new area calculated with this diameter, but it finally break at a load of 7 kilonewton. So the force was 7 kilonewtons over the new area. Don't use the old area because it was 20 millimeters when it was yielding and it attained the maximum load. But when it was finally breaking, the diameter reduced from 20 to 10, giving us this area. So we are using this area at the breaking point, 7 point. Therefore, the stress at the breaking point can give us 89.12 megapascal. Remember, it is the same as 89.12 mega Newton meter square. That's all for the example 1.5. You have to name or know where your forces are and the diameter to get your area. Let's move to the next example. Example 1.6. A concrete cube of 150 millimeter by another 150 by another 150 is loaded in a compression testing machine. You remember I explained the compression testing machine in the episode 2. If the compressive force, the force was compressive, acting normal to the one surface or one face of the cube is 250 kilonewton. Calculate the compressive stress in the concrete. The compressive stress. So let's see. We have a force acting in a compressive way. Let's assume this is the cube. It's an assumption. It was the forces were in compression. They were trying to squeeze the cube, and the force was 250 kilonewtons. Same here, 250 kilonewtons. Trying to compress this bar. But remember, since it is a cube, the volume is given. The three-dimensional space or length is given as 150 by 150 by 150. Let's list our parameters. We have a force of 250 kilonewtons. But here, the area, we know that area is two-dimensional as you get a length by a breadth. So the area for a cube, we can take any two of them and multiply, which is the length times the width or the breadth. So we can calculate the area. Remember, you are not going to multiply the three of them. If you do so, you are calculating for V, which is volume, L cube, but the area for the cube will be L square. So the area is L square. But here we can convert this to meters by dividing each of them by 1000. So the area is 150 on 1000 multiplying by another 150 on 1000. And I'm getting the area to be 0.0225 meters square. So the compressive stress, remember calculate the compressive stress. So stress compressive should be equal to the force over the area, which can be estimated as the force was 250 raised to the power 3 over the area of, we just saw the area here, 0.0225. This is newtons. This is meter square. Compressive stress. So we can say the compressive stress is giving us 11.11 megapascal. When you find for this, you're going to get 11.11 megapascal, or the unit can change. 11 mega Newton meter per second square. Mega 10 raised to the power 6. So it's very simple. You have to know that this is a cube with the volume given. L cube, the volume. But here we are looking for the area, since stress is force over area. We know that it was under a force, a compressive force of 250 kilonewtons. It was compressing this bar. So there was stress induced inside. The force is here. We have the area, the two-dimensional space. Since we want to convert the millimeter to meters, we divide by 1000, this by 1000, and it is giving us this, the force over the area, and we are getting. In most cases, you can negate this. So negative 11.11, since it is what? Compressive. Remember, compressive stresses are what? Negative. Whilst tensional stresses are what? Positive. But you indicate here stress compressive. So you can ignore the negative and just write a positive because you're showing it is compressive. Are we good? All right. Let's move to the next example. Example 1.7. Wow, this contains a lot. Let's pay attention here. A bar of circular cross-section is loaded by tensile force P of 85 kilonewtons. The bar has length 3 meters and diameter 30 millimeters. It is made of aluminium with modulus of elasticity E 70 gigapascal and Poisson's ratio V was 1 over 3. So the question is asking us to calculate the elongation, the decrease in diameter, and the increase in volume. If we are to assume the proportional limit of the material is not exceeded. Remember in the episode 2, I talked about the proportional limit where I explained the tensile test graph. So you can refer to the second episode. Let's get started. It's easy. A lot of staffs were given here. So we can assume the circular bar this way. Let's assume this is the bar. It was under tensile force. So there's a tension of 85 kilonewtons. So their stresses induced, there will be an elongation. The length will increase since it is under tensile force. So our parameters, we have F force to be equal to 85 kilonewtons. We have our length L 3 meters. We have our E to be 70 G. Remember this is a prefix times 10 raised to the power 9 PA. We have Poisson's ratio V 1 over 3, and we have the diameter to be 30 millimeters, which can also be 0.03 meters. So once we see the diameter, likely we are going to have area. So let's find the area for the first time. So area is equal to pi d squared on 4. And our area is going to be pi, our d is 0. I prefer the meters square on 4. And our area is giving us, what are you getting? I'm getting 7.068 10 raised to the power negative 4 meter square for the area. Now let's come to the question. Calculate the elongation produced. But from episode 2, we deduced the formula for elongation, where we said elongation is the force times the length over the Young's modulo times the area. So it can be given as elongation is FL on EA. But we have all these parameters, so we can just go straight forward. The force was 85 kilonewtons. The length was 3 meters. 3. The E, Young module, was 70 gigapascal, which is 70 times 10 raised to the power 9, positive 9, times the area. We had 7.068 times 10 raised to the power negative 4. And we are getting the elongation produced as 5.154 exponent 3 negative 3 meters as the elongation produced. So you have your formula, you have your force, your length was given, your E was given, and your area. Since you have the diameter, you can calculate for the area. Now let's look at this. The increase in volume. No, we are here. The decrease in diameter, change in D. The decrease in diameter for the circular bar. Let's look at this. Do you remember from Poisson's ratio? So this is I. From Poisson's ratio, we say V is equal to negative the lateral strain over the axial strain. Yeah, it is in the episode 2. You can check out for it. Poisson's ratio V is equal to negative the lateral strain over the axial strain. Are we good? But axial or lateral strain in the Y is called the lateral strain. It's giving us the change in the diameter over the diameter. While the axial one is giving us elongation over the length. So can we bring this into the formula and check out? So I can say V is V times the lateral strain is equal to negative of this. Negative because in Poisson's ratio, an increase in the lateral side will cause a decrease. An increase in the axial side will cause a decrease in the lateral side. That's why we brought this negative. So you can ignore and finally bring your answer as negative if you are dealing with the Poisson's ratio, because it is going to give you negative here and this negative will take out, giving you a positive answer. Check out for the episode 2. So if we are to bring the lateral strain sigma y, which is a change in the lateral side of the material, is change in diameter over the diameter, and this the axial strain, which is the elongation over the length. I'm going to get V, which is Poisson's ratio, elongation on length, equal to this. Let's ignore the negative because Poisson's ratio is going to be positive over the D. And the question says we should calculate the decrease in diameter, which is change in D. So let's make change in D the subject. And it's going to be this D times the Poisson's ratio and the elongation over the length. We have all these parameters there. We can do our substitution. So the change in D is equal to what's D? Diameter. From here, we saw that the diameter was 0.03. What V? Poisson's ratio, 1 over 3. Yes, we have Poisson's ratio to be 1 over 3. So I can bring it 1 on 3, and I have the elongation. What is the elongation? From the question, we've already calculated for the elongation. 5.154 times 10 negative 3 and over the length. What's the length? We have the length here, 3 meters over 3 meters. Therefore, the change in diameter is going to give me 1.716 10 raised upon negative 5 meters, or is going to give me 0.0176 millimeters. Are we good? Remember, if you're changing from meters to millimeters, you're going to multiply by 1000. And 1000 is 10 raised to the power 3. When you add it from indices, it's going to be 10 raised to the power negative 2. And this is how we are going to express it. So the change in diameter for this particular circular bar is going to be 0.0176 millimeters. You can also change the elongation as well to millimeters. But remember, I like working in the meters because it is the standard. Are we good? Now let's move to the next example. So example 1.8. The figure below shows one end of a beam resting upon a bearing pad made of rubber compound, and which is 250 millimeters square in plane area. If the vertical reaction at the end of the beam, wow, 3,000 kilonewton, that's huge. Calculate the compressive stress in the bearing pad. Now look at the figure. This is the beam. We have this beam resting on this bearing pad. You can see it from here. This is the bearing pad. The beam is resting on it. And we can also see that this pad is 250 millimeter in length and it is a square. So we are going to get something like this. Sorry, this assume is square. So here is 250 and 250. The same thing happens here, 250. So a square area and the reaction. So this beam is exerting force, a downward force on the pad. And remember, there will be a reaction also opposing this force in the upwards direction, causing a compression in the pad. So we have to calculate for the compressive stress induced here. So what do we do? Let's start listing our parameters. So from the question, we have the length to be 250 millimeters, which is the same as 0.25 meters. And the reaction, remember this reaction is a force which is acting. F is a force. Look at the units, kilonewtons or newtons. So we have our force F to be 3,000 kilonewtons. We have to calculate for the compressive stress, but we know that stress is force over the area. So once we have our length, we can find the area for a square area. Remember, it's a square. So the area for a square is L squared. That's the length times the length, because any length is equal to the other length. So we can have the area to be 150, sorry, 250 on 1000, because I want to convert this to meters. Multiply another 250 on 1000. And what am I getting for the area? I'm getting the area to be 0.0625 meter square for the area. So I have my area, I have my force. I can calculate for my compressive stress. So compressive stress force on area. Force is 3,000. Remember, it's kilo, still 10 raised to the power 3 newtons on the area 0.0625 meter square. So my compressive stress is giving me negative 448 megapascal. Or since you indicate here as compressive stress, you can just say this compressive stress is 48 mega, either pascal or Newton meter per second square. So that's it. You have to check the length, and it was a square in area. So we know that square in area is length times length. We know the force, the vertical reaction. As this force is coming down, there's an opposing force equal in magnitude to this force, and the reaction was 3,000 kilonewtons, which is the force. We just find the compressive stress as the force over the area. We do our substitution. This negative indicates a compressive stress, or you can indicate as stress compressive is 48 megapascal. You can choose to write all the digits, but as a scientist or as a mathematician, prefix is always recommended. So 48 times 10 raised to the power 6 Newton meter per second square or Pascal for this particular example. Let's keep moving. I hope it's becoming interesting. Let's look at this example. A metal bar ABC, this is ABC, having two different cross-sectional areas is loaded by an axial force P. The figure shows the parts AB and BC are circular. So anything we are going to do, we assume what? A circular part. Circular in cross section with diameters 50 mm and 38 mm respectively. If the normal stress in part AB, pay attention, the stress in AB just from this place to here is 40 megapascal. What is the normal stress in the part BC? Don't just say it is a continuous bar, so the stress here will be equal to the stress here. No, there will be different stresses induced in different segments. So let's look at how this goes. First, let's list our parameters. We have part AB, so diameter of we have the diameter of part AB to be 50 millimeters, which is equal to, let's convert it to so solution. We have diameter in AB, part AB to be 50 millimeters, which is the same as the diameter in BC was 38 millimeters, which is the same as 0.038 meters. Are we good? The stress, they give us stress in AB is equal to 40 megapascal. What else do we have? So once we have diameter, we can calculate for area. Are we good? So can we say area in part AB? We are going to do some analysis. Is equal by before we are calculating what we will need. The area in AB will be pi d square AB d square is 0.05. Someone will say, but we already have the stress in AB. Why area? You'll get to know on 4. So area in AB will give us, what's the area in AB? And use your calculator to punch this. You're going to get a value over here. So we have the area in meters. Are we good? Okay. So we can also calculate for the area in BC. So area in BC is also going to be pi the D square on 4. We're also going to get a value for that. Now let's look at the analysis. This is a beam, something like this, and it is fixed here. It is fixed here. So we have to draw a free body diagram by removing this whole bar from the end, and we are going to get something like this. Let's assume it's circular though, but we're going to get something like this. And this is the P, force P. Remember, when we remove this from the fixed end, there will be a reaction force opposing the direction of this force. So it's also going to be like this to keep the member in tension. Are we good? So here is AB and here is C. What do we need? We have the stress induced in AB already. We have the area here. Can we find the force AB? Are we good? We have the stress 40 megapascal in member AB. We know the area, so we can calculate for the force. Remember, what's the formula for finding force? We know that force in AB is equal to the stress in AB multiplying the area AB. So we have 40 mega, remember 10 with the power 6 times the area, the whole of this, what we got, pi square on 4. And I'm getting my force in AB to be 78 point kilonewton. So look at this. This is the induced force in member what? AB. This is the force here in AB. Remember, we cannot calculate for the stress in BC because we don't know the force here. We don't know the force acting on BC. We know it to be P, but what is the value of P? We don't know. So now we know the stress acting in member AB. We are able to calculate for the force also acting on member what? AB. Can we do some section? Can we open member AB and equate forces to get the magnitude of P? Yes, we can do it. So let's create a section. I'm going to cut member AB. So if I cut, I'm going to get a section like this. I'm getting something like this. Remember, this is the cut surface, AA. And since this force was in the opposite direction, P, it should be the force FAB, FAB also in this direction. So from the idea of forces, can we say this force, assuming this member is in equilibrium, this force is equal to this. So we can say P is equal to FAB. Yes, we can say that. So now we know force AB. Therefore, P is also equal to the same force, 78.539 kilonewton. So now we can see that this force P acting on member BC is actually 78.539 kilonewton force. Now that we know the force, we know the area, can we calculate for the stress in BC then? Yeah, we can do. So stress in BC is the force, which is 78 point. In our next video, I'll be teaching on how forces act in segments like this. So watch out. 0.9 kilo over the area. Remember, we are not going to use the area of AB because the diameters differ, 50 and 38. Although the same force here, we saw that it's acting in this member, but with different area, causing different stresses. So let's see. The area was, what did we get for the area in BC? We got pi d square, which is 0.038 square on 4. Therefore, stress in BC is giving me, what value are we getting? I'm getting 69.25 megapascal, approximately 69.3 megapascal. Good. So it's quite easy. You know the stress here and you know the area. We can make the force the subject and calculate for the force acting in member AB. Are we good? We cannot just say that the force here was equal to here until we did the section. Remember, when I remove the whole bar AB from this fixed end, I'm going to get this diagram. This P is going to act here. To balance this P, there should be another force acting this direction. And it's also equal to P. Are we good? So I know the force in member AB. I do my sectioning. Since this force is moving this way, and I made a car, there should be a force opposing it, which is the same as FAB. And we know that this P now is also equal to this, since this was equal to that. So we saw that P was also this, and we got our area from member BC, and we estimate the stress in BC. So are we seeing the stress in AB was 40 megapascal and the stress in BC is 69. The same force, but the area decreased. Let's keep moving to the next example. Example 1.9. You should pay attention here because this example contains a lot. Still, I'll be running fast. You can go back and check again. A steel pipe of length 1.2 meters, outside diameter of the pipe D2 was 150, and the inside diameter, remember a pipe, something like this. See that? Yes. So the outside diameter was 150 millimeters, and the inside was 110 millimeters. You get it? It's compressed and by an axial force 620 kilonewton. The material has modulus of elasticity E. This Poisson's ratio is this. First, we have to determine the following: the shortening, that means the elongation. I know the elongation, it can either compress or what? Elongate. By this time, the shortening, meaning there was a compression. Yes, it was compressed because you can even see from here. It was compressed. So let's list our parameters. Solution is quite interesting. You'll love it. There's strength of material. So the length is already in meters. D2, that's the outer diameter, was 150, which is the same as 0.15 meters. The D1, the inner diameter, was 110 and is the same as 0.11 meters. We have the force P. The force P, the compressive force, was 620. Wow, huge. And we have E, modulus of elasticity for the steel pipe. Remember, steel always have this 200 gigapascal, and the Poisson's ratio V is 0.3. Are we good? So what do? We are to calculate for the shortening. And remember, one shortening, which is the elongation, is giving us PL on AE, where A is the area of the pipe. But remember now we have two diameters. We have an outer and an inner one. So let's see how we can estimate the area. So area of the pipe is given by this formula. Pay attention here. We now have pi, the D is now, we have D2 square minus D1 square on 4. So we can see that the D, the diameter, to get the actual diameter, we must D2 minus D1 all square for the area. So we can estimate. So the area is going to be pi. D2 is 0.15 square minus 0.11 square, or you can bring all square. It's the same thing. All on 4. And I'm getting my area to be 8. You can check it out. Meter square for the area. So from this formula, I have my P already. Simple. I have my L, I have my E, and I have my area. And the problem was the A. How to know that they gave an outer diameter and an inner diameter. This is it. So the D here, the D square is going to be the larger one, which is the outer, which is greater, minus the inner one to get the diameter. Here, are we good? So the elongation now is equal to, I have my force, 620 kilo, 10 raised to the power 3. Multiplying the length, what was the length given? 1.2, or on area, 8.168. What was the Young modulus E? Remember the giga raised to the power 9. And I'm getting my shortening to be 4.55 times 10 to the power negative 4 meters. You can multiply by 1,000 to get the answer in millimeters. So this is the shortening. There was a decrease when the force compressed the steel pipe. There was this amount of compression produced. Very good. Let's go to the B. So this is for the A. The B part, the lateral strain. The lateral strain. Always lateral and axial strain can be obtained from the Poisson's ratio, where we know that V is equal to negative the lateral strain on the axial strain. Very good. But I said, or it is known that the axial strain is the elongation over the length. So we want the lateral strain. Can I say lateral strain? Let's ignore the negative because it is showing that this Poisson ratio is negative and it will come making the whole thing positive. So the L coming to multiply. So we are going to do cross multiplication here. So this is going to be V multiplying this. So lateral strain, can replace it by the V elongation on L. Very good. So the lateral strain is equal to, what is the V? 0.3. 0.3 multiplying, what is the elongation or the shortening? We've just calculated for it, 4 points. So you see, if this one is wrong, we're going to get something wrong, and it's going to be a cos 90 job over the length, which is 1.2. So the axial strain is going to be 1.138 times 10 raised to the power negative 4. Remember, no unit, because if this is the Poisson ratio is what? Dimensionless. And from this, we know that strain is also what? Dimensionless. So there's no dimension given. Let's check the C, the increase diameter 2 in the outer, that's the outer diameter. And we also have to calculate for the increase in diameter 1, which is the inner diameter. So there's a lot here. We have to calculate for increase in diameter 2, increase in diameter 1. So the C part, what do you think we can do here? Do you remember I said lateral strain is equal to change in diameter over the diameter? Yes, we are going to use this. But in this case, diameter 2. So change in diameter 2 over diameter 2. We already have this. We already know diameter 2. So we can just find the change. That's quite simple. So change in diameter 2 is equal to this. We just have it here. 1.138 10 raised to the power negative 4 multiplying the diameter 2. Diameter 2 in meters is 0.15. 0.15. And I'm getting change in diameter 2 to be, I'm getting it to be 0. You can use the 150 here to get it in millimeters, but you know I always work in meters. So if I'm to use the 150 millimeters, I'm going to get 0.01706 millimeters for the change. So the same thing happens to change in diameter. So there's an increase. Yes, there was an increase. You can see it's a positive value. There was an increase. Here there was a shortening, a decrease. You can see a negative value. Very good. Okay. So let's look at for A1. So the same thing. The lateral strain is the same as change in diameter 1 over diameter 1. So change in diameter 1 is equal to this, which is 1.138 times 10 raised to the power negative 4 times diameter 1 or 0. Or this millimeters. Let's get the answer in millimeters. 110 millimeters. So I'm getting change in diameter 1 to be 0.0125 millimeters. That's the change in diameter 1. There we go. So it's just a matter of we knowing the lateral strain and expressing it in this form. Now let's look at the D. I have a little space. I don't want to clean so that I can have the full view. D says the increase in the thickness, change in T, that's the wall thickness. But we are also going to follow the same step as whenever you are given, let's say, a circle or a cylinder form that has two diameters, the thickness, first the T, we are going to get the thickness as, we assume the first diameter, the higher diameter, diameter 2, minus the first diameter, all over 2 is going to give us the thickness. So our thickness T is giving us the 150 millimeters minus 110 millimeters all on 2. And I hope my thickness is going to be 20 millimeters. Are we good? So this is the thickness. Look, there's something like this. The thickness from this to this end, this is the thickness. Are we good? So you subtract the smaller one from the bigger one and divide it by 2 to get the thickness D or T to be 20 millimeters. And we have to find change in thickness. So we go through the same approach. So this continues this way. Thickness. So lateral strain is also changing thickness on thickness. So the change in thickness is going to be the lateral strain times the thickness. And we know that the lateral strain is the same thing. 1.138 10 raised to the power negative 4 times the thickness we just had, 20 millimeters. 20 millimeters. So the change in thickness is going to give me what value? I'm getting 2.276 10 raised to the power negative 3 millimeters. Yeah, this is in millimeters. You can convert it to meters later. So this is the solution for problem, for example, 1.9. It's quite easy. If you have any problem, let me know in the comment section and I will have it answered. Thank you for your attention, and next episode on axial loaded bars will be released soon. Subscribe to the channel and more videos are coming on your way. Thank you. My name is Ade Brown, Einstein Mechanics. Thank you.